So this new unit will encompass the overarching idea of a sequence. And in today's lesson, we need to be able to walk away with two things. Number one, if I give you a defined sequence, can we find specific terms and term values? And number two, going the opposite direction, if I give you a sequence, can you actually figure out what formula created that sequence? So let's talk about the idea or the definition. Loosely speaking, a sequence is just a list of numbers. They could be random, they could follow a pattern, but basically, if you make a list of numbers, congratulations, you have a sequence. Let's talk about the formal fancy schmancy definition, though. Definition of a sequence. So, a sequence is a function. Now, like a function, you usually give it a name. In function notation, we say f of x. I don't know why, but sequences typically start at the beginning of the alphabet. A, B, C. It just because one of those weird math things. So let's give this function name a. A sequence is a function a whose domain is the set of natural numbers. And if we forgot the definition of the natural numbers, they're basically the positive whole numbers. So that's the idea. Let's choose a different color. That's the idea of a sequence. The terms of the sequence are the function outputs, are the function values, are the function values. So if you have an equation or a function and it is a sequence, we'll call it A. If you were to plug in positive whole numbers, congratulations, you are finding terms of the sequence. So they're literally the function outputs. So they're the function output when you plug a 1 into the function. They're the function output when you plug a 2 into the function, when you plug a 3 into the function, when you plug in a 4 into the function, so on and so forth until you plug in a specific number, right? However, this is function notation, and technically a sequence is a function whose domain is the natural numbers, but because it's sort of its own special branch of mathematics, it's its own special thing, mathematicians just give it a separate notation. So the idea is that we usually write a sub n instead of the function notation a of n, right? So you know how function notation is usually f of x, g of x, whatever. Sequences, it is a function, so it's a sub n, n stands for a positive natural number. But instead of using function notation with this parentheses, we typically like to use subscript. So a sub n is the same thing. Hence, the terms of the sequence may be written as, so instead of a of 1, a of 2, a of 3, instead of that way, we can write a sub 1, a sub 2, a sub 3, so on and so forth, right? So, and I think the reason why mathematicians like this notation, in addition to the fact that it gives sequences its own separate thing, is that it has a better meaning, because in math we typically use subscripts as indices, as an index, as a as a label or a counting thing, right? It sort of tells you the position that the number is relative to the entire set. So the number, oh, the number a sub 1 is called, not surprisingly, the first term. Right? So a sub 1 is called the first term. A sub 2 is called the second term. Not surprising. A sub 3 is called, you guessed it, the third term. And so on and so forth. Dot, 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 until you get the nth, the a sub n is called the nth term. It's also called the general term, right? So this guy here has two names. So this is called the nth term. Actually, I'll use a separate color for him. He's sort of special. Or the general term. So that's the idea of a sequence. A sequence is nothing more than an equation. It's basically a formula. But what separates a sequence from a regular function is that in a regular function, the domain can look a variety of ways. The domain could be all real numbers. The domain could be just fractions. The domain could be, positive, negative integers. What makes a sequence is that the domain is specific. The domain is always the natural numbers. A sequence is always just a function where you're always plugging in 1, 2, 3, 4, so on and so forth into the input. For example, an example of a sequence. 2, 4, 6, 8, 10, 12, the multiples of 2, all the even numbers, is a sequence. Now, that list writes out the terms of the sequence, but we can sort of define it, or we can sort of represent it or describe it using an equation. And now we've already said it, right? It's the multiples of 2. So hopefully we can see that this sequence may be described by a sub n equals 2 to the n. Okay. How so? Well, let's go back up to the actual list here. I hope everyone can agree that we would say that this is the first number, 4 is the second number, 3rd is the third number, 8 is the fourth term, 10 is the fifth term, 12 is the sixth term, so on and so forth. We would say what I'm boxing here is the formula of the sequence because, well, what do you get when you plug in n equals 1? You get a 2, as expected. What do you get when you plug n equals 2? You get a 4, as expected. What do you get when you plug in n equals 3? A 6, as expected. So you can see here how a sub n equals 2 to the n is a formula that describes the sequence. We call this an explicit formula. Why do we call it an explicit formula? Is because whatever term I'm looking for the fourth term, I'm looking for the 17th term, whatever. All I have to do is plug in that term number into the formula and it'll give me the results. Now, there is another way to describe the sequence. I sort of, the first obvious thing that popped to mind is, oh, it's the multiples of 2. But some people might say, oh, this pattern, you're just adding 2 to the previous number. So we could actually describe this a separate way. We could have said a sub n equals a sub n minus 1 plus 2. Right? This is called a recursive formula. And the reason why we call it a recursive formula is because in order to find the very next term, you need to know what the previous term is. Because the verbal description of this sequence, you're always adding 2 to the previous number, is true, right? To get to 4, you had to add 2 to 2. To get 12, you had to add 2 to 10. To get 8, you had to add 2 to 6. So that description of, oh, this sequence is just adding 2 to the previous number is a true statement, but we call it recursive because we needed to know the previous number in order to find the current number. So that's sort of how you read this notation here. A sub n, the nth term, the formula, the general term, you can sort of think of it as the current term, and then n minus 1 would be the previous term. And what if I want the previous 2 terms? The term that's 2 numbers away will be n minus 2. And what if I want the number 3 numbers away? N minus 3, so on and so forth. Right? So both have their usefulness. I personally like explicit formulas better, but there are certain patterns where explicit formulas are hard and recursives are easy, and vice versa. There are lots of patterns where recursive is hard and explicit are easy. They're just two sides of the same coin. They're describing the same sequence. But to use them, it should be pretty straightforward, right? This is where explicit formulas shine, because explicit formulas, it's just like going straight to your result. So what are some things that you might be asked to do? You might be asked to find the first 5 terms and the 100th term of the sequence defined by a sub n equals 2n minus 1. And I'll put the solution in a different color. Okay. So this should be pretty straightforward. Notice it's an explicit formula because there's no subscript n minus 1. It's just straight up, here's a formula. Well, let's answer the question. It wants to know the first 5 terms. So I need to know the first term, the second term, the third term, the fourth term, and the fifth term. And remember that the index, the little n, tells you what term you want. So if I want to find the first term, a sub 1, you just plug a 1 in for the n. That's it. A sub 1 is 1. Right. The second term, just plug a 2 in for the n. The third term, just plug a 3 in for the n. The fourth term, plug a 4 for the n. And the fifth term, plug a 5 in for the n. So that's the power of explicit formulas. It's very easy. Now, if I want to find the 100th term, that sounds complicated. Oh no, 100, it's a big number. Well, it's child's play if you have the explicit formula, because all you got to do is just plug it in. So what's that, 199? So there you go. So easy peasy. Let's take a look at another one here. Say, I'll switch up the letters. Say b sub n equals negative 1 to the nth power over 2 to the nth power. Okay. But again, it shouldn't be hard. You literally just plug and chug. So it's the first term, b sub 1. Change all the n's, or substitute a 1 in for all the n's. So negative 1 to the 1 power is negative 1 over 2, so it's negative 1/2. b sub 2, negative 1 squared, 2 squared. So negative 1 squared is a positive 1, 2 squared is 4, so it's a positive 1/4. b sub 3, negative 1 cubed, 2 cubed is a negative 1/8. b sub 4, negative 1 to the 4th, 2 to the 4th is positive 1/16. b to the 5, or the fifth term, is negative 1 to the 5th over 2 to the 5th is negative 1/32. I'm going to go all the way back up here. And to get the 100th term, negative 1 to the 100th power over 2 to the 100th power. Quite honestly, 2 to the 100th power is a huge, huge number. So when you're doing these, if the number that you're going to get is just ridiculously big, it's going to cause an overflow error in your calculator. Just go ahead and leave it in non-simplified form. So this would be a positive 1 over 2 to the 100th power. There's something interesting about this sequence here. Let's start with the very first term here. So the first term is a negative 1/2, then it went to a positive 1/4, then a negative 1/2, then a positive 1/16, then a negative 1/32, right? So hopefully you guys notice that this thing is alternating between positive and negative, starting with the negative in this case. So negative 1/2, positive, negative, positive, negative. That alternating sequence was a result of having this here. So a negative 1 to an exponent in a sequence, his job is to just alternate the signs of the terms. So we notice that the terms alternated between positive and negative because of the negative 1 to the n in the formula. So that is the mathematical way of making something alternate. If you notice you have anything in math alternating back and forth between positive and negative, the likely culprit is probably going to be negative 1 raised to some variable exponent. What you're also going to have be asked to do on today's practice is to go backwards. If they give you a sequence, can you come up with the formula? Now, unlike the previous example where you can figure it out, you can do stuff to get the answer, these types of problems, I hate to say it, there is no magical formula, right? It all is intuition. It all is pattern recognition. It's one of those you either know it or you don't know it kind of thing. And the only way you can get better at it is if you build up the intuition, if you build up the experience with practice. So suppose they asked you to find the nth term of a sequence whose first several terms are given. Again, that phrase, the nth term, basically means find the formula or the equation. So let's see what the first pattern is. 1/2, 3/4, 5/6, 7/8, so on and so forth. So, and again, there is no calculation to do. You can't plug into a formula and it'll spit it out. You just have to look at patterns and be able to recognize patterns. So this is sort of like doing a crossword puzzle, right? You just have to figure out the puzzle. Now, what some things you should notice is, well, I noticed that all the terms are fractions, so I'm probably going to have a fraction bar in my formula. What else should we notice? Hey, we recognize that the denominators are all the even numbers. We've done that before, right? Those are the multiples of 2. So I know that the denominator should be 2 to the nth power. Next, what do we notice? Well, all these fractions are suspiciously similar, or the numerator and denominator are suspiciously similar. You have a 1 and a 2, 3 and a 4, 5 and a 6, 7 and an 8. Hopefully you guys notice that the numerator is exactly 1 less than the denominator. Well, since we've already said the denominator is 2 to the n, the numerator must be 2 to the n minus 1. So there you go, right? Again, we didn't do any calculations, we didn't plug into the formula, we just saw patterns, and that's going to be the idea of this section here. Now, with these types of questions, you should never have to wonder, oh, is it right or wrong? You should be able to generate the same sequence if you plug in n equals 1, n equals 2, n equals 3. So how do I know that this is the right answer? When I plug a 1 into the n into this formula here, if I plug in n equals 1, do I get a 1/2 out? If I plug in n equals 2, do I get a 3/4 out? If I plug in n equals 3, do I get a 5/6 out, so on and so forth? And in this case, we do. Let's do another one, part B. Find the nth term of the sequence -2, +4, -8, +16, -32, so on and so forth. Now, at first glance, b sub n equals, it looks like, hey, it's the multiples of 2, but not quite. This is 2, 4, it's not 6, but it's 8. It's not 10, it's 16, then it's jumping all the way to 32. I hope, again, this should be a pretty obvious, straightforward pattern, that these are not the multiples of 2, but these are the powers of 2. Instead of adding 2 every single time, we're doubling by 2. So I know it's going to be some sort of exponent. Now, what do you also notice? You should notice is that it's alternating. Right? Negative, positive, negative, positive, negative, so on and so forth. And as discussed before, if there's some sort of negative thing going on, it's probably going to be a multiple, or you're probably going to have -1 to the nth power somewhere. So by writing this down, I've taken care of the alternating negatives. I'm going to ignore those. And the pattern was, we've already said, that it's the powers of 2, so it's 2 to the nth power. Easy peasy. Okay. I would accept that as a correct answer. That's perfectly fine by me. Some mathematicians might simplify it since they notice that the exponents are the same, just regular n's. Properties of exponents, if you're multiplying, they have the same exponents, you can sort of like blend the answers together. So instead of saying -1 to the n times 2 to the n, it's simply -2 to the nth power. Both are equivalent. We have to remember, though, that the definition of a sequence is a function where the domain is the natural number. So you always start at n equals 1. So let's take a look at the same sequence, but slightly different. +2, -4, +8, -16, +32, so on and so forth. So we already know there's going to be a -1 to the nth somewhere. And we already know it's going to be 2 to the nth power, because those are the multiples of 2. It's the same thing. But here's why I sort of emphasizing the domain. These sequences, you always start at n equals 1. Well, if I plug in an n equals 1 here, right, I get -1 to the first power, which is -1. And -1 times 2 should be a -2. But in our actual sequence here, we started at a +2. And as a matter of fact, the alternating positives and negatives are the exact opposite. What went wrong, or what's going on here? Well, it turns out that in this particular sequence, we sort of want to delay the negative. We sort of want to offset the negative by one term. Mathematically, in the equation, the way you do that is you have to shift the exponent by 1. Now, in this particular case, it really doesn't matter. You can do n minus 1 or n plus 1 because the base number is -1. Okay. So by doing that subtle change, you successfully sort of shifted the negatives over by one term, and then this right here will definitely give you this sequence. So just remember that -1 to the nth power will always start off applying that negative. If you want to delay or shift applying that negative by one term, you either -1 or you +1. Explicit formulas, recursive formulas, it doesn't matter. I expect you guys to be able to be comfortable handling with them. And again, it's just straightforward plug and chug. Suppose I told you that a sequence is defined recursively by, now in a recursive sequence, they will always tell you one or several terms. So notice how in all of the, let me scroll up to the very first example. Notice in all of these examples, they just gave you a formula. Hey, a sub n is this formula. That's it. B sub n is this formula. That's it. In a recursive formula, they will always give you at least one starting number. So in this example, they tell you a sequence is defined recursively, so they're going to give you the first term. Hey, start at a sub 1 equals 1, and further terms, a sub n is going to equal 3 times the quantity a sub n minus 1 plus 2. And I'm going to ask you, find the first terms. Find the first 5 terms. Easy peasy, right? Find the first 5 terms. Well, the first term is easy. A sub 1 equals 1. They told you that. Now, a sub 2, I'm going to do this straight up mathematically, and then the others, I'll do it logically. A sub 2, notice, in its simplest form, a sub 2, a sub n. A sub 2 is just this formula, but plugging in n equals 2. So let's go ahead and do that. So this is 3 a sub 2 minus 1. I changed the n into a 2, plus 2, which equals 3 a sub 1 plus 2. Now that's not an answer because it's not a full number. But you notice how this guy here, this answer uses an a sub 1. So in order to get a final answer, I need to change that a sub 1 into a number. Well, if you look previously at their lists, we know what a sub 1 is. A sub 1 is 1, so we can do that substitution here. And that's what it means by recursive. 1 plus 2, which equals 5. Oops, sorry, forgot the parentheses. Man, too early today. That would be 9. That's what it means by recursive, in that in order to figure out what a sub 2 was, we had to use the a sub 1 number. Let's do it one more time. I sort of lied. We'll do this the full math way one more time, then the last we'll do it logically. So what's a sub 3? Well, a sub 3 is just this formula up here, but change the n into a 3, right? That's just regular plug and chug. So we have 3 a sub 3 minus 1 plus 2, 3 a sub 2 plus 2. So notice I can't answer this question unless I figure out what a sub 2 was. But we've already said that a sub 2 equals 9, so you can just plug that in. 3, 9 plus 2 equals, what's that, 11 times 3 is 33. In general, you can just know that, let me use a different color, that anytime you have subscript n minus 1, that just means the previous term. So when I actually do this, I showed my entire work for notes, but when I do this myself, I just remember a sub n minus 1 means previous term. So a sub 4 equals 3 times the previous term, which was 33, plus 2. All right, so just a little bit faster, less writing. So that's 35 times 3 is what, 90, plus 15 is 105. And then last but not least, a sub 5 is 3 times the previous term, plus 2. So that is, what's 315 plus 6 is 321. Right? So that's how recursive formulas work. Basically, you're going to have to use the previous numbers to your advantage. Now, again, when it comes to using recursive formulas, you always need at least one starting point. The rule of thumb is, however many previous terms the formula is defined by, that's how many seed numbers, that's how many starting numbers you need. For example, if f sub n equals f of n minus 1 plus f sub n minus 2, find the first 5 terms. See how in this recursive sequence, it's using 2 previous numbers, right? So n sub n minus 1 means the previous number. Sub n minus 2 means the previous second number. So since this formula is defined by 2 previous numbers, this problem is going to need to give you at least 2 starting numbers, and it does. Where f sub 1 is 1, f sub 2 is 1 as well. Right. So if we read this in plain English, doesn't this say that in this sequence, the term is the previous number plus the previous second number? So I'm going to do this logically without writing it all out. So let's answer this question. The first 2 terms are easy. They gave it to you. So f sub 3 equals, according to the formula, add the previous 2 numbers. So if I add the previous 2 numbers, 1 plus 1 is 2. F sub 4, add the previous 2 numbers. 1 plus 2 is 3. F sub 5, add the previous 2 numbers. 2 plus 3 is 5. Easy peasy. So recursive formulas, they're typically, in general, quote, harder than explicit, but once you understand them, once you know how to read them, it's a cakewalk to use. Right? So that's it. Have at it. Good luck.